You know, have you ever thought about a problem that's so tough, so fundamentally unsolvable, that the smartest people in the world just threw up their hands and said, nope, can't be done? Well, for 200 years, a math problem like that has stood like a giant mountain, basically telling us where human knowledge ends. So today, let's talk about this impossible problem and the wild new idea that finally cracked it.
So let's wind the clock all the way back to 1824. For the mathematicians back then, this was a huge year. It was the moment a line was drawn in the sand, separating what they thought was possible from what they were sure was impossible.
It's like they literally built a wall around what algebra was allowed to do. They made a formal declaration that some equations, once they got complicated enough, just couldn't be solved perfectly. And you know what? That became accepted fact. It was truth. But that leads to a pretty interesting question, doesn't it? I mean, what if that wall, the one that's defined the rules of algebra for 2 whole centuries, wasn't quite as solid as everybody thought? What if the foundation was, well, incomplete?
Okay, so this gets us right to the heart of it all, a 200-year-old impossibility called Abel's theorem. For generation after generation of mathematicians, this was pretty much the final word on the matter. End of story.
So the official name is the Abel-Ruffini theorem. And what it says is that there's no single formula to solve polynomial equations that are of the 5th degree or higher, at least not if you're only using what they call radicals. Now, radicals sounds fancy, but it's just the stuff we all learn in school. Adding, subtracting, multiplying, dividing, and taking roots, like a square root or a cube root. For any equation up to the 4th degree, yep, there's a nice, clean formula. But the 5th degree and higher, the theorem said, no way, impossible.
And listen, this wasn't some dusty, forgotten theory. Oh no, this was a fundamental belief. For 200 years, this idea drew the map of what was possible in algebra. It was taught in every university, written in every single textbook. The case, as far as everyone was concerned, was completely closed.
So you gotta wonder, why did they hit this wall? Why did these classical methods, which worked so darn well for the simpler stuff, just stop working? Why the dead end?
Well, it turns out the old toolkit just wasn't built for this kind of job. The best way to think about it is like trying to describe a sphere, a perfectly round globe, using only flat, straight rulers. You can get really close, but you're never going to capture its true curved nature. The math behind these equations gets so complex, it's like the existing keys just wouldn't turn in the lock. The complexity just explodes. So mathematicians had to settle for approximations, getting super close with endless decimals, but never ever reaching that pure, perfect, exact solution. And eventually everyone just sort of accepted it. Yeah, it's just impossible.
But one mathematician, Professor Mourad Sultan Ezouidi, he just refused to accept that. He basically argued that the equation was never the problem, the tools were. And this quote from him just nails it. The limits weren't a law of nature. They were a limit of the 19th century tools people were using.
And that whole perspective, that whole new way of looking at things, led him to create something absolutely revolutionary. A new theorem that completely changes the game.
I mean, just look at the difference here. It's night and day. Where the old method said impossible, Ezouidi's theorem finds exact, symbolic answers for unbelievably complex equations. Instead of fuzzy approximations, you get 100% verifiable algebraic answers. But maybe the biggest thing is the change in attitude. It completely rejects this idea of mathematical fatalism and basically says, nope, every single equation has a perfect answer just waiting for us to find it. So how on earth does it work? Well, instead of trying to find one single key to unlock the whole thing at once, this new approach is way more clever. First, it rearranges the equation into these nested layers, kind of like a Russian doll. Then it uses these really elegant transformations to simplify each layer, one by one. And finally, it just pulls out the exact roots. It's this beautiful, systematic process that lets the equation kind of unpack and solve itself. Which, of course, brings us to the ultimate test. Could this new theorem actually do what everyone said couldn't be done? Could it really solve the unsolvable? And here it is, a 20th degree polynomial. I mean, just look at this thing. It gives you a real sense of the crazy complexity we are talking about. For 2 centuries, getting an exact answer for something like this was pure fantasy. So this is the whole point. The old way would give you an approximation, right? A long string of decimals that gets closer and closer, but is never actually perfect. But the new way, the one promised by Ezouidi's theorem, delivers pure exactness. A clean, symbolic answer that is the true root, with no rounding, no estimating.
And that is exactly what happened. Using this recursive method, the exact symbolic roots of that 20th degree monster were derived. It proved that what everyone thought was a fundamental law of math was really just a historical misunderstanding. The impossible was now possible.
You see, a discovery like this is about so much more than just solving one really hard equation. This is about redefining what we even consider to be a mathematical truth.
So let's just break down what this really means. First off, it shows Abel's theorem wasn't wrong exactly, it was just incomplete. It was true, but only inside the small box of 19th century tools. This new work blows the doors off that box and expands the boundaries of algebra itself. It's a huge shift away from just getting close enough and back to the search for perfect, exact answers. And, maybe the most profound thing, it suggests that no polynomial, no matter how ridiculously complex, is actually unsolvable. I love this quote from the source. This discovery does more than solve an equation, it redefines what it means to solve. It's not just about finding a number anymore. It's about uncovering the deep, elegant, hidden structure inside the math itself. And that really leaves us with a fascinating thought to end on. If a 200-year-old mathematical wall can just come tumbling down like this, what other impossible problems out there, in science, in technology, in everything, aren't really impossible at all? They're just waiting for somebody, somewhere, to come along with a brand new way of thinking.